Python gives you several powerful ways to remove items from a list. Imagine we have a list of 3 files, and we need to delete file 2. The most straightforward tool available in the list class is the remove method. This method simply asks, which specific item should I delete? In this case, I have targeted file 2. That is the exact item we want gone. Watch what happens when we run this code. Our original list contained files 1, 2, and 3, but now only files 1 and 3 remain. File 2 has been successfully removed. However, you must be careful with the remove method if you try to delete an item that has already been removed. You can see us running this process multiple times. The only reason this works repeatedly here is because this variable is constantly repopulated with the same data. The remove method then cleans it up. But if I isolate the command on a separate line and try to remove file 2 again, what do you think happens? You will trigger an error stating the item is no longer in the list. This is why robust error handling is absolutely essential. Another excellent option is the pop method. Instead of a value, pop targets a specific index or position. Here, it will remove the item located at index 0. Running this reveals that file 1 is gone, leaving only file 3 behind in our list. But here is why the pop method is actually a game changer. It actually tells you which value it just removed. You can capture that item in a variable and continue to manipulate it elsewhere in your code. Finally, we have the clear method. It is simple and direct. It doesn't return a value, it just returns none. Its only job is to wipe the entire list completely. You are left with a perfectly empty list. So, remember your 3 core methods: remove, pop, and clear. Each has its own purpose. Just stay alert for potential errors. Pop can also cause issues if you aren't careful. If we keep popping index 0 until the list is empty, the code will eventually fail, specifying a position that does not exist. Will crash your program every single time. We previously covered removing single items from a list. But can you spot the major flaw in that approach? Look at our list here. We have multiple log entries. Do you think the remove method will clear them all at once, or only target the very first occurrence? Let's run it and find out. Any guesses? There it is. It only deleted the first instance of the word log, leaving every other duplicate untouched. Watch what happens next. If I comment this out and execute it again, it finally catches that second entry. But you had to run it twice. The program had to scan the entire list over and over again. It searches the first item, then the second, the third, until it finally reaches the fourth. This is incredibly slow. You should never do this. Instead, use list comprehension for a professional solution. Here's the same list we started with. But now, we aren't just removing one single item. We can filter out multiple values instantly. Standard removal methods simply cannot keep up. Look at this syntax. We are iterating through the list, checking every individual element. The item variable identifies each entry one by one. It loops through the data and reconstructs a list, keeping a value only if it is missing from our exclusion list. This condition is evaluated for every single entry. For every object in our set, Python only retains the value. If your specific requirement is satisfied, break it down like this. Here is your condition, here is your loop, and this is the result you get back. By running this, notice how we scrub the list of all unwanted items with incredible speed. Mastering this tool is essential to succeeding with Python. If the syntax feels new, rewatch this section to truly internalize how it functions. Don't settle for inefficient code. Code like a pro by using these powerful comprehensions. This syntax will save you hours of frustration, and its performance is second to none. Struggling with complex syntax? Let's master list comprehensions. If you are new to Python coding, this logic is an absolute essential. Master it now to stay ahead of the curve. This foundation will define your success. Look at this list of items. We want to strip out these 2 specific values from our dataset. Notice how some words, like log, repeat throughout the list, while others appear only once. List comprehension is a one-line powerhouse that does it all. Traditionally, you would create an empty list and loop through every item. So, for every entry in our current list, we check if it belongs in the remove values group. Then operator effectively scans our list for matches. If the item isn't there, it stays. It works like this. We add the valid items to our new collection. Once the loop finishes, we update our original variable. We are essentially replacing the old data with the filtered list. You don't even need a temporary name. This is the standard, long-form approach you see here. But list comprehension achieves the same result much faster. It returns the item directly. The loop is built right into the line. The syntax actually mirrors our logic word for word. Even our if condition fits perfectly inside the brackets. If the item isn't in remove values, it is instantly captured. The key is this: the major breakthrough to understand is that you no longer need the append method. You don't even need to initialize an empty list variable. You just get the item. This part is vital. This is the direct output of your entire statement. Compare the long version to this elegant shortcut. It might look unusual at first, but when you break it down, it's just a streamlined version, with several steps handled for you automatically. Forget manual appending or temporary variables. You are updating your data directly. When we run this, you'll see that log and temp have been successfully wiped from the list. The result is identical. You get the exact same output, but with much cleaner code. Let's dive deeper into list comprehensions. Does this code look like a mystery? Don't worry if you're feeling a bit lost. It's common to feel confused at first, but mastering this is the backbone of learning Python. Without it, your coding journey will be a struggle. Take a look at this list. The square brackets tell us exactly what it is. We're storing these values inside this variable. Now our goal is to take each item and multiply it by 2. But there's a catch: only if the number is greater than 2. That means we only want 3 and 4, just those two numbers. When we run this, the output is 6 and 8. Perfect. So how does this logic actually work? We start with a loop. This part here, for n in numbers. What is numbers? That's our original variable. And what is n? It represents each item as we cycle through the list. On the first pass, n is the number 1. Next, it becomes 2. Then it moves to 3, and so on. The value of n updates automatically with every step. The letter n is just a placeholder. Next, we add an if condition. This checks if the current value of n is greater than 2. We're scanning the list and testing every single number. If a number passes the test, it moves to the next stage. That's where we multiply it by 2 to get our final answer. Python then saves that transformation into a new list variable called result. When we print result, look at the screen. There is our finished list. This is called transformation. One part filters the data, and the other part changes it. All of this happens inside a list comprehension. It allows you to filter and transform data to create a brand new list in one elegant line. I hope this finally clears up the confusion around this syntax. If this clicked for you, make sure to like and subscribe for more coding gems. During your everyday social media scroll, let's finally demystify big O notation. You have likely seen this symbol before. It features an O and N and sometimes a squared symbol. But what does this actually mean for a Python beginner? O of N simply means we are making one single pass. But this notation, it represents a repeated, full pass. Let's look at a practical example. Don't worry if it seems complex, it's easier than you think. Imagine a simple list of items. This list contains 3 letters, A, B, and C. We want to loop through and print each one. A standard loop looks like this, for item and items. Perfectly simple, we just print the item. Running this gives us a clean output. Letter A, letter B, and letter C. This is what we call a one-pass operation. You are looping through the list exactly once. In big O terms, that is O of N. Now, let's take it up a level. What happens if we nest our loops? Watch this. It gets interesting. We want to repeat the entire process for every item, starting with the first letter of letter A. When we grab A, we don't just print it and move on. We trigger a brand new loop. Let me show you the result. For every single letter, we run the list again. Instead of one pass, we have a nested sequence. Look at the first character, A. For A, we repeat the entire set, A, B, and C. Then we do it all over again. Check out this output. It tells the whole story. Notice how the first letter, A, triggers 3 lines. That is because our inner loop has 3 items. We finish that and step back out. We grab the next letter, which is B. And for B, we do the exact same thing. The inner loop prints A, B, and C again. Finally, we arrive at letter C. Once more, we loop through every single letter. With 3 items, we've now repeated the work. Once here, twice here, and 3 times here. That totals 3, 6, 9 operations. And what is 3 times 3? Exactly 9. That is what the squared symbol represents. It is effectively 3 squared. 3 squared equals 9 total steps. And that is the power of n squared. Let's take a quick detour into the math, because mastering this logic is key to leveling up as a top-tier Python developer. You have likely seen big O notation before, but you might still wonder what it actually means and how to calculate it. Let's break it down with a clear example. Imagine we have a list of items. If you iterate through these letters A, B, and C and print them one by one, you are essentially making a single pass through the entire list. In big O notation, we represent this as n to the power of 1. But in practice, we usually simplify the syntax. We don't actually write out the power of 1. It simply means if you have 3 items, 3 times 1 equals 3 total operations. Now, watch what happens when we run this. You see the output: letter A, letter B, and letter C. But what if we loop through the items twice? Notice the change when I run the code now. We start with the letter A in our outer loop. Then, in the inner loop, we repeat the process for A, B, and C. It creates a pairing. You get these combinations: against A, against B, and against the letter C. Then it moves to letter B and repeats the cycle for A, B, and C. This pattern continues through the entire list. Essentially, you have 3 operations for the first item, 3 for the second, and 3 for the third. That's 3 plus 3 plus 3, which equals 9. In shorthand, that is n squared. It means you are multiplying 3 by 3. Because for every item in your list, you are running another full inner loop. That gives us 9 total steps. That is quadratic complexity. So, how do we reach cubed? Mathematically, it looks like this: 3 times 3 times 3. That is what cubing actually signifies. We know 3 times 3 is 9. And 9 times 3 is 27. When you have this structure, with an outer loop and a second nested loop, just like before, but now we add a third. Can you imagine the scale now? Look at the results. We have generated a massive list of operations. If we were to count these manually, and I'll just paste this into a new window to show you, how many lines of output do we have? Exactly 27. And remember our math? 3 times 3 is 9, and 9 times 3 is 27. That is n to the power of 3 in action. 3 levels of nested repetition. That is the essence of big O notation. 27 total operations for just 3 items. The notation continues to scale this way. If you added another level of nesting, it would become n to the power of 4. 4 levels deep means even more complexity. 2 levels is squared, 3 is cubed. And with no nesting, it's just linear time. This applies to any number of items. If you had 4 items instead of 3, the linear version would just be 4 steps. But n squared would be 4 times 4, 16 steps. And n cubed? That's 4 times 4. Times 4 again, which skyrockets to 64. I hope this demystifies how these notations directly impact your code's performance. If this explanation made a click for you, don't forget to hit like and subscribe. Ever look at code this clean and wonder what's the catch? It looks perfect, right? You know exactly what it does. You have a list of items and you want to filter some out, specifically the letters A and C. So what could possibly be wrong with this logic? Wait until you see the performance hit. This is incredibly inefficient code. Don't scroll away yet, this is a lesson you will use forever. It is a total game changer. The bottleneck is the dot remove method. To fix this, we need to master big O notation. We have 5 items in our list, just 5. A very small sample, right? To remove A and C, we loop through the list. Simple enough. But then we call that dot remove method inside. Here's the secret. Remove is a loop itself. It scans the entire list again to find set value. You are looping through items, then looping again just to remove them. That hidden second loop is where your performance dies. With 5 items, we are looking at 5 squared. That is 5 times 5. Meaning 25 operations for a tiny list. That is n squared complexity. Now, check out the list comprehension method. We take the same list and the items we want to drop. We use a single filter to keep only what we need. It is fast, it is elegant, and it is built for speed. This leaves the remove method in the dust. Instead of dragging down the list, we build a fresh one. This distinction is crucial. Dot remove alters the original list in a slow way, while list comprehension creates a new, optimized version. It grabs what you need and moves on instantly. Efficient and clean. Look at the results. In big O terms, the first way does double the work. This second method? Way faster. Imagine the scale. If you had 10 items, 10 times 10 is 100 operations. As your data grows, that repetitive work explodes. But with this, you only pass through once. Just 10 operations. Compare that to the 100 needed for dot remove. That outer loop combined with the inner search is a killer. Want a deep dive into Big O? Check out my previous video for the full breakdown. But admit it, you just learned something huge. Keep this in your toolkit for your next project. Ever wonder why Python's remove method is so sluggish with large lists? And what makes list comprehension so fast? Let's dive under the hood of the remove method. Imagine we want to strip the letter from this specific collection. You'll notice our target A is sitting right here in the third slot. The remove method starts by hunting down that letter A. Once it finds it, step 1 is deleting it entirely. But here's the catch. In step 2, it has to slide the letter D over into that empty space and reorganize the entire structure. We are looking at two heavy operations happening at once. Let's visualize this process. Look at indices 0, 1, 2, and 3. This is our starting point. It deletes the target and forces every element to the right to shift left. Now, D has migrated to the third position. It's a double hit to performance. First the deletion, then the expensive task of shifting everything. Think about removing the very first item, the letter B. Every single item in the list we have to move, one by one, toward index 0. That is a massive overhead. List comprehension, however, builds a brand new list from scratch. You loop through items, apply a quick filter, and generate a fresh result. It's clean, lean, and efficient. Once the new list is ready, you simply point your original reference to this optimized new version. This is why the remove method is a performance killer for big data. Processing millions of records? Avoid it at all costs. Stick with list comprehension instead. Now you know the secret of Python's internal list management. Never forget that two-step drain. Locate and remove, then shift and realign. Master these steps and your code. Let's master the basics. You might have been doing this the hard way for years. Or perhaps not. Regardless, this is vital. Python's remove method seems great at first. To delete an element, like the letter from this list of characters, it looks straightforward. We start with our original list. And now the letter has been deleted. Perfect, it works. You might wonder, where is the problem? It looks fine, right? Here is the catch. The remove method is actually quite fragile. If you check the documentation, it raises a value error if the item is missing. This means you need bulky error handling everywhere. That is bad practice. Let's try to remove a letter that isn't there, like G. G does not exist in our list. Running this triggers a crash, item not in list. Since G is missing, the whole program stops. How do we fix this? More complex code? What if you need to remove multiple letters? Say you want to remove both G and A. How would you handle that? It's getting complicated, isn't it? There is a better way. List comprehension comes to the rescue. I have been championing this for a long time. And for good reason. It is one of Python's most elegant features. Let's achieve the same result more cleanly. Watch as is removed. Notice the syntax here. We have a loop and a filter combined. This condition filters your list on the fly. It creates a brand new list with only the items you want. The unwanted letter is gone. Now let's try that missing letter G. You can run this as many times as you like. 0 errors. The code works flawlessly. What about removing multiple items? With the old method, you'd need multiple lines, but with this, just include the extra characters in a list. It iterates through and seamlessly excludes A and G. They are simply gone. You can even add a third, like the letter D. Even if you make a typo, like using a lowercase d, your program will not crash. It just keeps running. Always choose comprehension over outdated methods. If you want to master this, watch my deep dive videos, where I break down this syntax in detail. I've just given you a powerful reason to learn it. The best time to start is right now.